exponential and logarithmic equations. So we're going to put it all together here. We want to solve exponential and logarithmic equations, including applications. So let's remember what we already know that's going to be helpful. We know that the exponential equation and the logarithmic equation are inverse functions. Y equals b to the x is the exponential function, and x equals log base b of y is the equivalent logarithmic function. We know the property of the equality of exponents. If b to the x equals b to the y, then x equals y. In other words, if the bases are the same, then the exponents are equal. And we know a variety of properties or rules of logarithms. I've highlighted 4 here: the product property, the quotient property, the power property, and the property of equivalence of logarithms. Okay, in general, solving exponential equations algebraically is often done by 1, applying the property of equality of exponents. We'll do an example of that. 2, rewriting them in their logarithmic form. We'll do an example of that. Or 3, applying the equality property of logarithms. If m equals n, then the log base b of m equals log base b of n. Solving logarithmic equations algebraically is often done by either 1, rewriting them in their exponential form, and again, that's right up here, or 2, applying the equality property of logarithms, which is this one. In this case, it would be if log base b of m equals log base b of n, then we can say that m is equal to n. Let's get started. I've got a number of examples lined up for you so you can get plenty of practice in. Okay, solve 5 raised to the x minus 1 is equal to 0.07. Okay, so 5, the exponent is x minus 1 equals 0.07. Notice we need to find, or we need to solve for the exponent. So let's rewrite it in its log form. This is the base. This is the exponent, so this is the argument. Log base 5 of 0.07 is equal to x minus 1. Let's do a quick check to make sure we got it right. It is x minus 1, right? It is x minus 1. Let's do a quick check. Remember a little circle, 5 base raised to exponent equals argument. So we know that we've gone from here to here correctly. So now I can add 1 to both sides, and x is equal to the log base 5 of 0.07 plus 1, which comes out to, I believe, approximately negative 0.65. Let me double check that. Let's make sure we've got that. I'll tell you, we can double check that with a graph. Let's see. So we can check this in 2 ways. We can put this answer into here and see if the left side equals the right side. Or we can always solve these things with graphs. y1 equals this side and y2 equals this side, and where they intersect is the answer. Let's solve it graphically. Okay, so I'm in my y equals, and let's have y1 equals 5 raised to the x minus 1, and let's have y2 equal 0.07, and let's see where they intersect. There's the log function in blue, and in red here, almost on top of it, is the exponential function. They obviously are pretty close. Let's zoom into the origin there and see what's going on. Zoom in, not zoom out. And let's see if we get a better sense. There's the log. And there it is crossing. It's coming in from above and it's crossing there. So let's go to second calc intersect. And let's see if the answer is approximately negative 0.65. Sure enough, negative 0.652291. So I rounded that to the 100th there. Okay, let's keep going. Give me a moment to get my act together on this end. Okay, example number 2 is an example that we're going to apply the equality property of exponents. Solve 8 to the x is equal to 4 to the x squared minus 1. Well, these bases are not the same. One is obviously 8 and one is obviously 4, but they're both powers of 2. And so let's recognize that. 8 is 2 cubed and 4 is 2 squared. So I can rewrite it. 8 can be rewritten as 2 cubed. And then I have the x. The x is the exponent here. And 4 can be rewritten as 2 squared. And then let's put the exponent in there, x squared minus 1. Okay, well, I gotta use my property of exponents that when I raise a number to an exponent, I multiply the exponents. So on the left is 2 to the 3x, and on the right is 2 to the 2x squared minus 2. Multiply 2 times x squared minus 1, 2x squared minus 2. Now I have the same base, and the equality property of exponents tells me that I can set the exponents to be equal. So 3x is equal to 2x squared minus 2. And this is the equality property of exponents. You know those, right? You know that one, right? Okay, this is a quadratic. I have a degree 2. The way we solve quadratics is we set them equal to 0. So 2, oops, I got to put a, and I'm going to move the 3x over here. So 2x squared minus 3x. I moved the 3x over, but I'm writing it on the left. Minus 2 equals 0. Okay, it's a trinomial. If you see that it's factorable, you can factor it. If it's not factorable, we can use our quadratic formula. I, of course, made this one so it's factorable. I know the answer, obviously, and I can factor this as a minus 2 and a plus 1 like that. So x is equal to, this one's negative 1/2, or x is equal to positive 2. Those are my two possibilities. Okay, I can check these. I put both of these numbers into here and see if they work. Well, the 2 is pretty easy. 8 squared is 64. 2 squared is 4. 4 minus 1 is 3. 4 to the third power is also 64. So the 2 I can check very quickly, mentally in my case. Let me get my focus back on here. There we go. The negative 1/2, I'm not very good with negative 1/2 exponents. So let's see if we can graph that one and see if that gives us a negative 1/2. So back to my y equals, and my left side was 8, whoops, got to clear it out. 8 raised to the x power. And I'll graph the left, excuse me, that's the left side, 8 equals 8 to the x. I'll graph the right side as y equals 4 raised to the x squared. Goes into that exponent, and then we'll subtract 1. And I'll do a zoom standard to start out. And there's my first function. And here's my second one, I think. Well, where is it? Oh, it's still, there we go. Okay, there we go. I'm still, you can still see I'm still circling here. There we go. Well, it turns out that if I were to kind of scroll up here or change my window, the 2, I already checked the 2 mentally, and the 2 is, here's 2 here. It's going to be a little bit higher, it's way up there someplace. At 64, of course. I'm only going to positive 10. But I wanted to check the negative 1/2. So let's zoom into the origin. And there's my 8 to the x power. And then here comes my 4 to the x squared minus 1 in red. There we go. I want to check this intersection, this answer right here. So second calc, the intersection enter, 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 and there's the -1/2 right there. So there's the other solution I could not check mentally. Okay, solve that one using the equality property of exponents. Let's take a look at this one. Okay, example 3. Solve 5 times the log base 6 of 7x plus 1 equals 10. I'm going to solve this one in 2 ways. Okay, so the first one, I'll write it down. 5 times the log base 6 of 7x plus 1 equals 10. I'm going to divide both sides by 5. I'm going to divide the left side by 5. That's a 1. And the right side by 5. This is the easiest way to solve this one. I have the log base 6 of 7x plus 1 is equal to 2. And now I have my log isolated. I'm looking for the answer to the argument. So I'm going to rewrite this using the exponential form. And this is my exponential form as we know. 6 to the second power is equal to the argument, 7x plus 1. Well, this is 36 is equal to 7x plus 1. Subtract 1 from both sides, and 7x is equal to 35. Divide both sides by 7, and 35 divided by 7 is 5. So there is the simpler of the 2 ways, and I'll let you check that. You can put 5 into here and see if this gives you 10, or you could check it graphically, have y1 equal the left side and y2 equal the right side, which is 10, and those 2 lines or curves should intersect at 5. The second way says, so I'll start here, and you can pick which one you like better. This way is a little bit more complicated, but that's okay. The second way says that I can use the power rule and move that back to there. So I have the log base 6 of 7x plus 1 to the 5th power is equal to 10. Okay, now I can change it to its exponential form because my log is separated, it's by itself. And this is 6 to the 10th power, well, that's a big number, is equal to 7x plus 1 to the 5th. Well, 6 to the 10th, I've already done that with my calculator. That is, wow, big number. I think it's million. 6,046,000, nope, it's 60 million. 466,176, yeah. 100,000, 10, yeah, 60 million equals 7x plus 1 to the 5th. I then take the 5th root of both sides, and I have 36 is equal to 7x plus 1, and that should look familiar from this side. Subtract 1 from both sides, and then divide both sides by 7. And so I'll do that in one step because I already have the work over here. Obviously, that's a little bit longer, but if that's what you prefer, that's totally fine. It gives you the exact same answer. In this case, I used the power rule here, and then I used the inverse exponential form to get to here. This one I first used division, and then I changed it into its exponential form, its inverse form to get to here. Either way works just fine. Okay, let's continue. I have some more examples. Lots of possibilities for how to do these things, and it's nice to see a variety of examples of things you're going to run across. So, we want to solve this one. The natural log of 2x minus 1 minus 2 times the natural log of 4 equals 3 times the natural log of 2. Well, I have logs on both sides, and I don't have any single number running around. So if I can get the left side, down to 1 log, I could then use the equality property of logs and just drop the logs and get right to an algebra problem. Well, first, let's take care of these powers. So we use the power rule to get these powers out of the way. So I have the natural log of 2x minus 1 minus the natural log of 4 squared, and that's just a number, is equal to the natural log of 2 cubed. And again, this is our power property or our power rule. Okay, now I'm going to go ahead and simplify these two and just make them numbers. I'll leave them as natural logs, but 4 squared is, of course, 16, and 2 cubed is, of course, 8. Looks a little nicer. Okay, now I have a difference of logs, and that is the quotient rule or the quotient property. A log minus a log is equal to the 1 log of the quotient. Okay, that is natural log of 8. And I know that this is just some number. So this is our quotient property or our quotient rule. Call it what you like. And now I have a log equals a log, so I can drop them. If the log of A equals the log of B, then A equals B. So 2x minus 1 over 16 equals 8. And that is the equality rule. And now I'm good. I'm just solving it algebraically. Let's multiply both sides by 16. 2x minus 1 is equal to 128. Let's add 1 to both sides. 2x is equal to 129. And then let's divide both sides by 2, and I'll leave it as a fraction. 129 divided by 2. Okay, so how do you check it? Well, 2 ways. Put 129 divided by 2 into here and see if this minus this gives you the same answer as this. Or you can solve it graphically, have y1 equal the left side, have y2 equal the right side, and where they intersect should be where x is equal to 129 over 2, which I think is 64.5. Looks like that's going to be, they'll intersect at x equals 64.5. I hope I did that right. There's the 6. Yep, that's it. Okay, let's do some application problems. Mathematics is applicable after all. According to one model, the number n of Americans, and we're dealing in millions, so our number represents millions, age 65 and older, that will have Alzheimer's disease T years after 2015 is given by this exponential function, n equals 5.1 times 1.03 raised to the t power. In what year will this number reach 8 million? Okay, so here's my function. It's an exponential function because I have a variable in my exponent. N equals 5.1 times 1.03 raised to the t power. And I want to know the time and what year that we reach 8 million. So I want my n to be 8 million. So 8 is equal to 5.1 times, 1.03. Let's clean that up. Raised to the t. One equation and one unknowns, I can solve it. Before I can switch this to the log, the inverse function, the log function, to get at the exponent, I need to get that 5.1 out of the way. It's being multiplied, so let's divide it. Okay, I'm going to leave it. I'm going to leave the number as 8 over 5.1. I'm not going to do it and result in an approximation. I want to get the real answer, and I'll round later. So 1.03t is equal to 8.51. We want to find an exponent. So let's rewrite it as a log. Base, exponent, argument. So the log base 1.03 of 8 divided by 5.1 is equal to t. There we have it. And we can check this. 1.03 to the t equals 8.51. So we've correctly written this, an exponential function, in its equivalent logarithmic function. We just did a quick check. Base to exponent equals argument. Put this into a calculator, and t is equal to, and I think I rounded to the 100th, 15.3 years. Remember, t is number of years after 2015, so years after 2015. So in what year will it reach 8 million? Okay, so 2015 plus 15.23 is equal to 2030.23. So it's going to reach it after 2030 by a little bit. So the answer is it will reach it in 2031. It won't reach it in 15 years. It won't reach it in 2030. It'll reach it just past 2030. Well, the year just past 2030 is the year 2031. Okay, let's do 2 more examples that involve application, and then we'll be all done. Alrighty, example number 6 here. The compound interest formula, we've seen this before. A, the accumulated value of a sum of money is equal to the principal times 1 plus the rate in decimal form divided by the number of times compounded per year, all of that raised to the number of times compounded per year times the number of years. How long will it take $50,000, which is the principal, how much we're going to deposit, to grow to $1 million, which is how much we want at the end, at an annual rate of 9% compounded monthly? Okay, let's remind ourselves that 9% as a decimal is 0.09. We need to write it as a decimal so we can do math with it. So here's our formula. A is equal to P, 1 plus R over N, all raised to the NT. So we won $1 million. Who doesn't want $1 million? And we're starting with $50,000. The rate is 9%, 0.09. We're compounding monthly, which means 12 times per year. And we're going to raise that to the 12 times t. So we're looking to find an exponent, which means we're going to want to rewrite this in its logarithmic form. But we need to get rid of this part first to get this over. So let's divide both sides by 50,000. That's a 1. I'll divide this side by 50,000. And I'm also going to do this math here, and I'm going to go out a number of decimal places. I don't really want to carry that. And so I'm going to go out a bunch of decimal places. I think I'm going to go out 4 or 5 because I'm not done with the problem yet. So this on the left side is 20. 1 million divided by 50,000 is 20. This in a calculator to 4 decimal places is 1.0075. And here's raised to the 12t power. So now I have my base to an exponent equals a number. I need to get at the exponent. So let's use the log function and write it in its inverse form, its log form, so that we can solve it for the exponent. So this is the base. Base. This is the exponent. So this is the argument. So log, the base is 1.0075, and there's my 20 is equal to the exponent. Okay, and let's double check. Did I go from here to here correctly? Base to exponent equals argument. So my little circle helps me remember that I get this correct. And I did. And so now I'm going to divide both sides by 12. And t is equal to the log base 1.0075 of 20 divided by 12. Well, that's not bad. Our calculator can handle that. And our time comes out to be approximately 33 years. I think I rounded that to the nearest year, and I got about 33. Okay, let's get one more in there, and then we'll be all done with this lesson. I'll get enough height here for you. Okay, medical research indicates that the risk of having a car accident increases exponentially as, I bet this should be the word as the concentration of alcohol in the blood increases. Well, that makes sense. As more alcohol gets into your bloodstream, more alcohol in your body, the risk of having a car accident, if you drive, obviously, goes up, and it goes up quickly the more alcohol you drink. This risk can be modeled by this exponential function. The risk is equal to 6 times e to the 12.77 times x, where x is the blood alcohol concentration, and r, which will be a percent, is the risk of having a car accident. Okay, what blood alcohol concentration corresponds to a 17% risk of a car accident? Okay, well, here's my exponential function, 6e to the 12.77 times x. I want to r is equal to 17%, and it is as a percent, so let's put 17 in there. And I have 6e to the 12.77x. Okay, I have an exponential piece. I have a variable in my exponent that I need to get at. I want to rewrite it in its log form, but that requires getting rid of anything that's attached to it. So I'll divide both sides by 6. And again, I'm going to leave 17 over 6 and just work with that as a number. And I'm going to choose not to round it. If you want to do the math and get a number, you want to go out to at least 4 or 5 decimal places if you're going to round, to give yourself lots of possibility if you need to round at the end. So you want to go out a bunch of decimal places. I'm going to leave it. So now I have base, exponent, argument. I can rewrite it. Now, I'm going to rewrite your choice. This is a base of e. That means I can rewrite it as log base e. Log base e. The argument is 17.6, and the exponent is 12.77x. Now, I did this so I can see it. Base to exponent equals argument. I can clearly go from here to here. But we also know that log base e is simply the natural log, so I can then just say, you know what, that's just the natural log. And there's an e is assumed. You could do like that too if you wanted to. It doesn't really matter, but you do want to check to make sure that you've rewritten the exponential form correctly in the logarithmic form. Okay, so I'm here. Let's divide both sides by 12.77. So the natural log of 17 over 6 divided by 12.77. And x is the blood alcohol concentration. And in this case, we get a blood alcohol concentration of approximately 0.08 as a blood alcohol concentration. So there you have it. Quite a few examples. Just be careful as you're, show your work. Be careful. And as my suggestion is, as you're rewriting from exponential to log or from log to exponential, you check yourself and you make sure you've done that correctly.